It is a pleasure to be here, and it's really, really nice to see that the GCCM Subsea Masterclass has become a solid cornerstone of the event. Willie George here in the audience, I know very well how he, helped to initiate this, and I'm really proud and thankful to be part of the GCCM Subsea Masterclass again. I'm old enough to have been in a time when there was not even a mobile phone, let alone a smartphone. And you will remember, if I look around, some of you will remember the old Nokia bricks, indestructible. But I was extremely excited. I remember it still very, very well. I had my first iPhone, the very first iPhone on the market, 3G, 2.5G. And I was going through one of these big towers, and I had 3 megabit per second. I still have the screenshot, 3 megabit per second. To me, that was amazing. And I remember it was raining, you would go, it was raining, and you would just check, where are the clouds, where's the rain? You could go online, you could check out internet web browser, you could make a picture, you could listen to music. It was everything in your pocket. So as a little bit of a preamble, I was very excited to see the news a few days ago that NVIDIA is investing a significant amount of money, taking a material interest in the company of Nokia. And if you read through the press release and all the bulletins, it was about bringing AI to your pocket, not just the mobile phone, but AI to the pocket. It's about, I'm not going to talk about that, but the fact that these giants work together and they will bring AI to the RAN tower and bringing basically AI inference in your pocket. That's amazing. That's the next step, which we will see happening, including 6G and so on. But for now, I'm going to be shifting gears. It will be a much more technical presentation about coherent pluggable optics, a little bit future-looking. And it's going to be very technical, so I hope the public doesn't mind. It's going to be optimizing subsea terrestrial networks. It's about what are coherent pluggable optics, what are the use cases, and some conclusions. So, submarine networks exist for more than 150 years. We have the Morse code, and in these 150 years, essentially, things have not changed. Even though the speed of transmission has increased 1 trillion times, the way it works is still you have some destination where information originates, it goes to the landing station, it's being regenerated digitally, and then it's transmitted over the submarine network. That hasn't changed. We now live in an era where the people among you, the architects, who need to come up with a better design, more flexible, lower cost, more efficient, more yield, have these challenges. And I'll give you an example of these challenges. Cable landing stations, they need to exist for more than 25 years because that's the lifetime of a cable system, of a submarine cable system. So if you build a landing station, you need to think far ahead. Now, not long ago, with transmission technology, you could create a solution with a whopping 4 terabit of capacity in one rack. Well, it was quite dense. So that means that for one fiber pair, you would have multiple racks. And if you go into landing stations, you still see some of that older technology there. So this means that in a cable system, until recently, cable systems had multiple fiber pairs. AE1 has 5 fiber pairs. So if we take a 6 fiber pair system, you can see automatically how this scales. Nowadays, spatial division multiplexing cables provide up to 24 fiber pairs, and it will go on. It can double even to 48, and you can immediately see. I visualized how this scales up. This is one of the busiest places in the world, Singapore. You can see how many cable systems terminate there. These are the cable systems currently terminating. And below you can see all the new cable systems coming up. And of course, we have Djibouti here, we have southern Egypt here, and we start to have new landing stations. We have Salalah, we have Muscat, and we see more and more cable systems being terminated there. The challenge is, and not many people realize this, is that on the one hand, we have innovation of technology, which doubles the baud rate approximately every 4 or 5 years. A new generation comes by the suppliers. This will halve or significantly reduce the number of transponders and space you need. On the other hand, the bandwidth is shown to grow every 2.5 years by 100%. So the pace of bandwidth growth outpaces the innovation cycle. So this means that just introducing the latest technology is simply not sufficient in terms of predicting what the needs are of a landing station. Now, to take a holistic view, there are basically 3 approaches to a submarine networking architecture. You can simplify the cable landing station, you can mix subsea and terrestrial, or you can make both sections as optimized as possible. So let me talk you through them. To simplify the landing station is something that is being introduced more and more. It simply means you basically deploy transmission equipment at the edges of your network. You bypass the landing station. You just have some optical amplifiers there. They don't need much space. They don't need much power. You can achieve significant spectral efficiencies and capacity, say 800 gigabit line rate and 150 gigahertz spacing over 7,000 kilometers. That's quite significant. But because you have an end-to-end connectivity, it basically means that the bottleneck is going to be the smallest amount of spectrum available, which is going to be the submarine cable system, because of the technologies being used in the cable system. So you eliminate digital regeneration in the landing station. So basically you get rid of 2/3 of all the equipment. You reduce the space and power, so that's a big advantage, but you do not have a most optimized capacity because you have the longest reach and the smallest amount of spectrum available. The second use case is where you basically digitally regenerate the signal in the landing station and you deploy C plus L band solutions on the terrestrial backhaul. That basically scales the terrestrial capacity, and you can use it in a flexible way. You can superimpose an end-to-end subsea network with a terrestrial meshed network on the L-band. That's a very efficient way of using your fiber plant infrastructure, which can be very expensive. It also means you have a better cost ROI in terms of investment of your fiber plant. The third approach is to basically optimize your network in terms of spectral efficiency and capacity end-to-end. In which case, again, you digitally regenerate, you ensure that the subsea connection is terminated in the landing stations, giving you the shortest reach, the highest capacity, and you have typically a completely separate terrestrial backhaul, where you have C plus L or even super C plus super L, and that triples the amount of capacity. So that means you can actually double or triple your subsea capacity on a single fiber plant. In terms of investments, that's very efficient. A fiber plant, a terrestrial fiber pair, can save you millions. And here's some of the metrics. Now, this is specifically important because if, for some of you who were here in the morning, listened to the panel, right, or even our previous presentation, we now have more redundancy. We have more flexibility in terms of end-to-end connectivity. We are learning about Middle East corridors, where you go from Salalah to Aqaba, Duba, or where you go from Bahrain to Yanbu. There are different paths. And this means that the terrestrial backhaul is an integral part. It provides redundancy, and you need to include that in your holistic end-to-end terrestrial subsea architecture designs. In summary, we have the end-to-end approach, we have the mixed approach, and we basically have the divided approach where you optimize terrestrial and subsea independently. What is relevant here is that to enable this in a cost-effective way, we need to look to what the technology can provide us in terms of optimization. Most of you have heard about the Shannon limit. The Shannon limit basically tells you that if you have amplifiers in a network, it doesn't matter if it's a terrestrial network or a subsea network, basically if you put in that network, you have a theoretical limitation of capacity that cannot be exceeded. The best transponders in the world can only converge to it, come as close as possible, but basically not exceed this. We do have higher and higher baud rates. We have line rates of up to 1.2 terabit, 1.6 terabit. Very soon, we're going to have 2.4 terabit. There will be new material being introduced to achieve these high baud rates. But in terms of getting more capacity, more asset value, more revenue opportunities for your network, we're going to be very limited in terms of incremental capacities. We are converging to what is maximum possible. This means that the priority of increasing capacity on a per fiber pair reduces. Instead, what we are doing is we're looking at more fiber pairs, and that's a significant cost, or more fiber pairs in terrestrial and more fiber pairs in a subsea network with spatial division multiplexing. Of course, cost and ease of operations remain a priority, but more and more the focus is on reducing reducing power consumption and floor space. What we are seeing now is a very interesting technology trend of coherent optical pluggable optics. What is a coherent pluggable optic? A coherent pluggable optic is basically a transponder the size of a matchbox. You have the electrical interface, you have the electronics, you have a digital signal processor, and you have the transmit-receive optical sub-assembly. And what these do is essentially the same as a transponder, which is, in terms of power consumption, at least 10 times as much, and in terms of size as cost, the same. So you have the optics, you have an indium phosphide photonic integrated circuit, which has the laser, which has the photodiodes, Mach-Zehnder modulator, and everything. You have the digital signal processor, which does probabilistic constellation shaping, which is something very new, just a few years old in transponders, is also now becoming available in coherent pluggable optics. Forward error correction, variable baud rate, and so on and so forth. In terms of coherent pluggables versus coherent embedded engines, we see that pluggable optics reduces power by 60%. The pluggable optic itself has 90% less power. The total environment gives you a significant 60% power reduction. An embedded transponder solution does give you higher spectral efficiency, simply because the DSP, the optics, are of a much higher quality, and they're much faster, so they are more sophisticated, can run slightly sophisticated modulation formats, and so on and so forth. So it gives you a better performance. If you look at the power consumption breakdown, actually what's interesting is that the DSP is not the most power-consuming unit inside a coherent pluggable optic. It's actually the serializer, deserializer, basically the translation between what goes into the subtending equipment and what goes out into the line port. Coherent pluggable optics, of course, are also constrained in terms of the format, the pins, the power it can take out of the subtending equipment, and the heat dissipation. And there are, of course, all kinds of standardization bodies. There's the Optical Internet Working Forum, which defines the ZR and ZR Plus standards, where the pluggable optic needs to comply with. Now, what is very important here is it's not just technology. Coherent pluggable optics are seen by hyperscalers as the way forward for their network infrastructure. So here on the left-hand side, you see basically blue is traditional optical solutions, and orange are investments in new optical solutions. And these are the hyperscalers. And you can see that investment in deployment of future equipment and solutions, the investment in traditional solutions is being kept. The investment in new type of solutions is increasing, and new type of solution is IP over DWDM, which makes use of coherent pluggable optics, as well as the projected increase of volume of new generation ZR and ZR Plus coherent optics. Why is this important for you? It's important for all wholesale operators because hyperscalers are a dominant force in the market. They are responsible for about half or more of the global internet capacity requirement. They have the means to deploy cable systems, and they are also, I think, a most important market driver. So essentially, we are all competing with hyperscalers. Even if hyperscalers do not provide wholesale services to the market, we are competing with them, which means that if they choose for a certain technology, and if that drives volume significantly, and therefore drive down cost, it means that even if that technology is maybe not the highest performance technology, it's certainly the lowest cost. And if you have a cable system and you want to have the best capacity, but you are not able to sell that capacity, you're basically left with an empty infrastructure. So going forward, I see wholesale operators going to make a choice in terms of, do I use high-performance embedded optical solutions, transponders, or do I use the lowest cost solution in order to compete with the prices in the market? So coherent pluggable optics are going to be relevant. Now, of course, there's a difference between the two. An embedded transponder, the traditional transponder, it gives you the best capacity. It allows you to aggregate multiple clients into one high-speed line. It allows you to have a demarcation, to do lawful intercept, service level agreement, and so on. And it has all kinds of technical functionalities. You can do optical protection, and so on and so forth. The downside is they are big, they are power hungry, so therefore they're not very effective in terms of operational cost. IP over DWDM traditionally is based with pluggable optics directly in the routers. So it gives you a significant advantage in power consumption. You don't need any additional space because it's embedded in the third-party equipment. But in terms of operational maintenance, it's much more complex. How do you manage pluggable optics in your customer's equipment? Where's the demarcation? The solution to this are thin transponders. Thin transponders gives you the best of both worlds. Thin transponders are white or gray transponders without optics embedded. You can put in client optics and you can put in coherent optics on the line side. It gives you the lower power, it gives you lower capex, smaller footprint. It still allows you to aggregate multiple signals, and it gives you, most importantly, it gives you a demarcation point where you can do your service level agreement, where you could do your lawful intercept, and so on and so forth. Of course, it's based on pluggable optics, so it does not give you the best spectral efficiency. In terms of, and this is based on a study of a standardized length, a reach of about 1,000 kilometers. It's based on a typical hyperscaler deployment, full spectrum. And in terms of metrics, when I say lower footprint, lower power consumption, you need to think about 24 to 40% of cost savings, 36% of power consumption savings, 50% footprint savings with a reduced capacity, which is roughly 15 to 25%. So this solves some problems or challenges we will be facing, cable landing station challenges, as well as how to provide a lowest cost service into the market. What does a thin transponder look like? A thin transponder is just like a transponder. It fits in a regular chassis, but you can put coherent pluggable optics into it, so you can scale the capacity you need. This is an example of 400 gig with 100 gig optics, LR4. This is an example of 800 gig optics on the client and on the line side. And because this is a submarine masterclass, right? The SLT, or submarine line terminating equipment, in a box allows you actually to deploy a very compact solution which includes all of the technology. We talk about the WSS, AZ idler, MUX, DMUX, as well as optics. So if you need maximum capacity, you can stack these. But if you have a need for a solution with a minimum capacity, you can actually have a pizza box SLTE solution that will serve all your needs. So where do you deploy the coherent pluggable optics? One option is you put them point-to-point, landing station to landing station on a submarine cable system. At this moment, the current generation 800 gig pluggable optics, just available, can be deployed on submarine cable systems with a reach of anywhere between 2,500 up to 4,000 plus kilometers. However, if you go to the highest and the longest reach, there are certain limitations in terms of how many channels, how much capacity can you deploy. There are some tricks being used to make certain you go longer. Next generation 800 gig pluggable optics, which will be available in about 2 years from now, will go transatlantic. And that's going to be a very significant game changer. Alternatively, you can deploy pluggable optics on the terrestrial backhaul. And I will show you in a bit more detail what that is about. To help you make a choice between coherent pluggable optics and transponders, I have devised this flowchart. And it's not a matter of coherent pluggable optics replacing transponders. That will certainly not happen. It's a matter of providing you, the architects of the network, or the people responsible for business operations, with a choice. So if you have a very long cable system, 10,000 kilometers or more, next generation coherent pluggable optics will still not be capable of supporting such distances. So you end up with a transponder. If you have a very old cable systems have 25 years of lifetime. We want to exploit that to the fullest. And some cable systems, 10 years or more older, are so-called dispersion compensated systems. That requires special nonlinear compensation algorithms. And current DSPs in pluggable optics are still not capable of handling that. So that means you need to consider traditional embedded solutions. If you have space power constraints, then you already noticed that coherent optics, pluggable optics, are a game changer. And otherwise, it's going to be a choice. Do you want lowest cost, or do you want high spectral efficiency? And it's not a matter of or, it's a matter of and/or, because you can choose to run with coherent pluggable optics, and then at a certain time, when capacity becomes more important, you can transition into embedded transponder solutions, which by that time might have evolved to even better performance. And this is not just science fiction. I mentioned current generation coherent pluggable optics can already bridge thousands of kilometers, and Nokia has actually been selected by submarine operators to transit such areas like the Mediterranean. So coming back on pluggable optics over terrestrial backhaul, right? You can put pluggable optics in the landing station. You can use them to convert wavelengths, basically to explore C+L band. That will basically double the capacity of your terrestrial system, or even triple, allowing you to put multiple subsea fiber pairs over a terrestrial system. And again, I will remind you about all these Middle East corridors. So that makes very efficient use of your line equipment. And if you do not own the fiber plant, it will save the wholesale operator millions of dollars in terms of fiber plant cost. In addition, it will maximize the subsea capacity. And I'll give you a study here at the lower left side, where if you have a backhaul from the landing station to the data center in combination with a long submarine cable system of 6,000 to 9,000 kilometers long, it means that a span or two spans of about 150 kilometers, which is the 30 dB at the bottom, 30 plus dB, will actually reduce the capacity of your submarine cable system by 15% or more. So basically, having an end-to-end backhaul optically expressed through the landing station, that actually reduces the capacity and the value and the revenue opportunity of your very expensive submarine cable system. So that is an additional value that coherent pluggable optics as a wavelength conversion in the landing station brings you. Actually, if the submarine cable system is shorter, the effect of a terrestrial backhaul is actually much larger. So the benefits of having a regeneration in the landing station in an effective way is much higher. Conclusions? Well, first and foremost, I hope this presentation has given you some insights in how ZR+ coherent pluggable optics have actually matured over the last few years and is bringing us a very impressive performance that you can use as a building blocks, as a solution building block with your architecture. Coherent pluggable optics brings several key advantages. Of course, power and space savings, as well as CapEx savings. You can embed them directly into routers. For most wholesale providers providing a service to the market, that might not be an option, but it's possible to investigate with your customers or even to do that with your own infrastructure. On the other hand, this does not mean that coherent pluggable optics will basically completely change the way we are doing networking. Transponders will remain in place, especially for ultra-long reach. Trans-Pacific, for example, Singapore to Egypt, 9,000 kilometers, 10,000 kilometers. For older cable systems, which are nonlinear in nature. And of course, if you have a somewhat older cable system where you want to maximize your capacity, embedded transponders is your solution as well. So basically, it will give you more choice, and it will allow you to either optimize in terms of performance or optimize in terms of cost. Thank you very much. I started a little bit earlier, so I wasn't really too much worried about the time, but I also know now I think we are at the end of the time. Bartosz, do we have time for a question? He's so sorry, but I did this on purpose, of course, so now at least I don't need to answer very difficult questions, but I will go outside, and if you have certain questions, please do not hesitate to approach me. Thank you. Thank you.